Hello everyone, my name is Madjar and today with our team we are going to explain the topic of advanced algorithm is the substring search. So substring search includes four main algorithms. This is the brute force, Cruz, Morris, Pratt, Bayer Moon, and the last one Robin Carr. So let's go.
Hello everyone, my name is Ilaman Karagali. Today we look at the topic of Rabin-Karp algorithm. Rabin-Karp algorithm is a string searching algorithm created by Richard Karp and Michael Rabin that uses the hashing to find any of set of pattern strings in text. Before we start, let me explain what is substring is of a string of the string. Substring of a string is another string that occurs in, for example, man is a substring of yellow man. Not to be confused with subsequence, because cover is a subsequence of the same string. In other words, any subset of consecutive letters in a string is a substring of the given string. Let me explain how Rabin-Karp algorithm works. Rabin-Karp algorithm. In Rabin-Karp algorithm, we will generate a hash of our pattern that we are looking for and check if the rolling hash of our text matches the pattern or not. If it doesn't match, doesn't exist in the text. If it doesn't match, we can guarantee that the pattern doesn't exist in the text. However, if it does match, the pattern can be present in the text. To calculate hash, at first we need to use prime number. This can be any prime number which you want, and after we define value of our letters in the text, like A is 1, B is 2, C is 3, like that, and so on. After and in the end, we determine hash value using the formula, this formula. In this formula, n is our text and p is prime number. Let's take as an example. One second. Let's say we have a text Kazakhstan, okay, and we want to find out if the pattern that in the text exists in the text. Let's take the prime number. Prime number is 11, and it's our formula, and this one is the value of our letters. We take value of the first letter of our pattern. First letter is Z, and the value of Z is 26. We take 26 and multiply it to the 11 to the power of 0. And we take the second letter. Second letter is A. Value of A is 1. We take 1 and increase it, multiply it to the 11 of power of 1. And we take last letter is K. Value of K is 11. We take the 11 and multiply it 11 to the power of 0, and we get this one. This is in the end we plus all the value, and we have a hash value of our pattern. When we get hash value of our pattern, we do the same things with the first 3 letters of our text. We do all things which we do with pattern, and we see that this value doesn't match with our pattern. So the strings doesn't exist there here. Now we need to consider the next step. To calculate the hash value of our next string, and next string is other, we can calculate this using our formula, but that will be not original and cost us more. Instead, we use another technique. At first, we subtract the value of first letter of previous string from our current hash value. First letter of previous string was a k, okay, and the value of k is 11. We subtract this and we get this one. We divide the difference with our prime, which is 11 for this example. We divided it and we get this one. After that, we take this number and do the same as on the formula. We take the next letter is a, from our text, and multiply it by our prime number, multiply it to 11 to the power of 2, and we get this one. This is hash value of string other, but we see is the new value isn't equal to our pattern's hash value, and we moving for k, and we get string z, and we do the all things we was do before that, and we have same hash value. It's a match, and this both string match. The substring exists in the string, and we return the starting position of our substring. That's all. It was example how to work Rubin cap algorithm, and this one you can see hash calculation code, pseudocode, hash calculation pseudocode.
My name is Yalaman. First, our algorithm reports, and I'm going to explain. In a voice method for substring search is to check for each possible position in the text at which the pattern called match, whether it does in fact match. The search method below operates in this way to find the first occurrence of a pattern string but in a text string txt. The program keeps one pointer I into the text and another pointer G into the pattern. For each I, it researches G to 0 and increments it until finding a mismatch or the end of the pattern G equals to M. If we reach the end of the text in I equals n minus m plus 1 before the end of pattern, then there is no match. The pattern does not occur in the text, or our convention is to return the value n to inside it in a match. In a typical text processing application, the G index rarely increments, so the running time is proportional to n. Nearly all of the comparators find a mismatch with the first character of the pattern. For example, suppose that you search for the pattern in the text of this paragraph. There are 191 characters up to the end of the first occurrence of the pattern, only 7 of which are the characters. So total numbers of characters compressed is uh, 191 plus 7 for an average of 1.036 compressed per character in the text. On the other hand, there is no guarantee that the algorithm will always be so efficient. For example, a pattern might begin with a long string of as if it does, and the text also has long string of as, then the substring search will be slow. Proposition force a substring search recurs nm characters compares to search for a pattern of length m in a text of length n. In the worst case, proof a worst case input is then both pattern and the text are all as followed by a b. Then for h of the n minus n plus 1 possible match position, all the characters in the pattern are checked against the text for a total cost of m. Normally, m is very small compared to m, so the total is nm. Such degenerate strings are not likely to appear in the English text, but they might will occur in other application, for example, is binary text. So we seek better algorithms. The alternative implementation at the bottom of this page is instructive. As before, the program keeps one pointer I into the text and another pointer G into the pattern. As long as they point to match characters, both pointers are incremented, the code performs precisely the same characters compared as the previous implementation. So understand it not that I in this code maintains the value of ig of I plus g in the previous code. Uh, it points to the end of the sequence of all right matched characters in the text where I pointed to the beginning of the sequence before. If I and G point to mismatching characters, then we back up both pointers G to point to the beginning of the pattern and I to correspond to the moving the pattern to the right on the position for matching against the text. So thank you for your time.
My name is Madjar, and now I am going to explain you about Bayer-Moore substring search. When backup in the text is not a problem, we can develop a significantly faster substring search method by scanning the pattern from right to left when trying to match it against the text. For the implementation of this algorithm, we can use the sentences of Bayer and Moore. It was designed by Robert Bayer and Jim Moore in 1977. So generally, assignment of the computational complexity of the modern vision of the Bayer-Moore algorithm is Pico multiplied by
n divided by m, where is n is the length of this string in which search is performed. M is the length of the search pattern. So next, consider the figure at the bottom of this page, which shows a search for the pattern needle in this text. Proceeding from the right to left to match the pattern, we first compare the rightmost E in the pattern with the N, the character at position 5 in the text. Since N appears in the pattern, we slide the pattern 5 position to the right to line up the N in the text with the rightmost N in the pattern. Then we compare the rightmost E in the pattern with the S, the character at position 10 in the text. This is also a mismatch, but S does not appear in the pattern, so we can slide the pattern 6 position to the right. We match the rightmost E in the pattern against the E at position 16 in the text. Then find a mismatch and discover the N at position 15 and slide the right 5 positions as at the beginning. So finally we verify moving from right to left starting at position 20 that the pattern is in the text. This method brings us to match position at the cost of the only 4 characters compares and the 6 more to verify the match. So before we implement our algorithm, we need to know about starting point. So to implement the mismatched character, we use an array right that gives for each character in the alphabet the index of its rightmost occurrence in the pattern. This value tells us exactly how far to skip if the character appears in the text and causes a mismatch during the string search. So to initialize the right, we can consider this example. At the first we need to create a right array and add them all the characters of alphabet, then give him index. If our character like A, B, C it isn't in our pattern, we give him -1 index. And if the character like D in our pattern, give him rightmost position we take and give him his index. And we can see this with character E. We have 3 E's in our pattern, but we use the rightmost E, which index is 5, and we give him index 5. So next, there we can see Bayer-Moore substring search implemented in Java. This is a Bayer-Moore substring search algorithm implementing in Java. So I'm going to explain how it works. With the right array pre-computed, the implementation, this algorithm was straightforward. We have an index I moving from the left to right through the text and an index G moving from the right to left through the pattern. The inner loop tests whether the pattern aligns with the text at position I. If the character in our text with index I plus j is equal to character in our pattern with index j for all j from m-1 to down to 0, then there is a match. So in the other ways, there is a character mismatch, and we have one of the following 3 cases. If the character causing the mismatch is not found in the pattern, we can slide the pattern j plus 1 position to the right, increment I by j plus 1. Anything less would align that character with some pattern character. Actually, this move aligns some known characters at the beginning of the pattern with known characters at the end of the pattern, so that we could further increase I by pre-computing in like this table, KMP table. So next, if the character C causing the mismatch is found in the pattern, we use the right array to line up the pattern with the text so that character will match its rightmost occurrences in the pattern. To do so, we increment I by j minus right with index C. Again, anything less would align that text character with a pattern, character it could not match one to the right of its rightmost occurrence. If this computation would not increase I, we just increment I instead to make sure that the pattern always slides at least one position to the right. So the bottom example in this figure you can illustrate this situation. So in the end, let's consolidate our knowledge and consider other example. And now you can pause this video and decide it yourself. So we have a pattern, this pattern, and we need this find this substring in this text. So the first we compare rightmost character of our pattern and this O. It isn't equal, but O character O in our so we have this pattern and we need to find it in this text. So the first we compare these two characters, E and O. It isn't equal, but O we have in our pattern, so we shift until this both O is match. So it would like this, and we again compare A with E. It isn't equal, and A not having our pattern, so we shift 7 position to right, like this, and then here we see T and the T in our pattern, so we shift our pattern until it is match. So we can see E H T is equal, but H and F isn't equal, so we shift 1 position to right, and there we again see that A and the E isn't equal. A is not our in pattern, so we shift 7 position to right and see that we find our substring in this text. So thank you for watching. It was a Bayer-Moore algorithm. Thanks. Goodbye.
Hello everyone, my name is Eldor Makambayev and I'm going to explain Knudsen-Morris-Pratt substring search algorithm. So, in computer science, the Knudsen-Morris-Pratt string searching algorithm, or KMP algorithm, searches for occurrence of a word V within a main text string S by employing the observation that when a mismatch occurs, the word itself embodies sufficient information to determine where the next match could be, thus bypassing re-examination of previously matched characters. KMP is an algorithm which checks the characters from left to right. When a pattern has a subpattern appears more than one in the subpattern, it uses that property to improve the time complexity and also for in the worst case. You would be able to independently cope with the task of finding a string in a line and would look like this. You would compare a character from a text character from a string, and in the case of a mismatch, you would move the string one character along the text so that until there is a string in the text or the text does not mean that there is no string in it. This approach is called brute force. The Cruz-Morris-Pratt algorithm also compares a character from a text of character from a string, and in the case of a mismatch allows shift by more than one symbol. The whole of this approach has a positive effect on the efficiency of the algorithm. In terms of software implementation, we have an index that indicates the character in the text and an index that indicates the character in the string. In case of a mismatch in the direct search, our string is shifted by one character and the index on the line is rolled back. When the KMP algorithm works, if there is a mismatch, we have a string shift and the index on the line never roll back. Mm, the algorithm the algorithm was conceived in 1970 by Donald Cruz and Wolfram Pratt and independently by James Morris. This was the first linear time algorithm for string matching. The three published in jointly in 1977. Independently, in 1969, Matevich discovered a similar algorithm coded by a two-dimensional Turing machine while studying a string pattern machine recognition problems. This is a source code for the KMP substring search algorithm. You can pause and see the code. The constructor in this implementation of the Knut-Morris-Pratt algorithm for substring search builds a differ from a pattern string to support a search method that can find the pattern in a given text string. This program does the same job as the brute force method, but it runs faster and faster for patterns that are self-repetitive. Proposition Knut-Morris-Pratt substring search accesses no more than a main character to search for a pattern of length m in a text of length n. Immediately from the code, we access each pattern characters once when computing DFA and each text characters once in the worst case in search. The KMP matching algorithm uses degenerating property pattern having same subpattern appearing more than once in the pattern of the pattern and improves the worst case complexity to ON. The basic idea behind KMP's algorithm is whenever we detect a mismatch after some matches, we already know some of the characters in the text of the next window. We take advantage of this information to avoid matching the characters that we know will anyway match. So, lastly, the linear time worst case guarantee provided by the KMP algorithm is a significant theoretical result. In practice, the speed up over the brute force method is not often important because few applications involve searching for highly self-repetitive patterns in highly self-repetitive text. Still, the method has the practical advantage that it never backs up in the input. This property makes KMP substring search more convenient for use on an input stream of undetermined length, such as standard input, that algorithms recurring backups, which need some complicated buffering in this situation. Ironically, when backup is easy, we can do significantly better than KMP. Next, we consider a method that generally leads to substantial performance gains precisely because it can back up in the text. So that's all. Thank you for your time.